Welcome, this is the AP Physics Workbook solution. Here I'm covering Unit 3, Circular Motion and Gravitation, Section 3.G, which is on mass and friction 4. Alright, here's the scenario. Consider a coin of mass m is placed on a rotating surface on a distance r from the axis of rotation. The surface rotates with a period t. There are some locations on the surface where the coin can be placed and the force of static friction will not allow the coin to spin. At other locations, the coin will split off because the static friction is not strong enough to prevent the coin from slipping. The coefficient of static friction between the coin and the surface is defined by mu. Okay? Alright, so part A. The dot on the right represents the coin when the coin is at locating shown in above. Draw a free body diagram labeling all the forces exerted on the coin. Make sure you do the relative lengths. Alright? And if you need help on this, check the notes from the section above this, right? Where I like the car and the track, and to give because there's notes on this. But there are 3 parts here, okay, and it's pointing inwards. If you look, it's pointing in, okay, because if you take a look, there's a force inwards, which is going to be the force of friction. The force of friction is what is producing the centripetal force here, okay? So right here, we're going to draw it to the right. And this is the force of friction. All right. What is holding it down? 1, 2, 3, 4, 5, 6. I try to draw as straight as possible. Fj. And going up. 1, 2, 3, 4, 5, 6 is Fn. All right. Good. That's it. That's all you need. There are 3 forces. All right. Starting this, right, they give you the deviation. And an inequality has been derived that must be satisfied at all times that the coin does not slip off the surface. The deviation has been done for you. You just have to fill in the annotations, okay? All right. So, what does this mean in English? All right. This means the force of static friction. The force of static friction is less than or equal to the, okay, this is the force of friction, which is less than or equal to the coefficient of static friction, right, times the normal force. Good? Right? Because that's what Fn is. Here they just made the substitution. It's the coin is on a horizontal surface. So the normal force is equal to mass times, can I fit it? No, I can't. Times gravity. All right, which is just mg here. All right, there's no cosine or sine part. If it's banked, then yes, it would be. Okay, here they made a substitution. It looks like the force of friction became mv squared over r. Okay, so the force of friction is providing is the force of friction, the force of friction is what is providing the centripetal force in this situation. In this situation, okay? Situation. I think that's how you spell it. Situation. Okay? So the mass, the The centripetal force um, has the substitution of the centripetal force replaces or substitutes in for the force of friction. That's not even how I spell friction. For the force of friction, right? So the mv squared over r is what the F of friction becomes in this case, all right? Next, here the mass cancels out, all right? Next, they multiply by r to both sides. So here they multiply r to both sides. So the radius, so the velocity, right, is a function of the coefficient of friction in this case is the coefficient of static friction and r and the radius. All right. Because notice when you see v is all by itself, and the only thing on the right hand side that can change is mu and the radius. That's why I said it's a function of the static coefficient and the coefficient of static friction and the radius. All right. So here you want to square roots both sides. Okay. All right. So you want to, from there to there, you multiply. Good. There you're going to square root both sides. From there to there, you're going to square root both sides. All right. Okay. Um, to to solve to get the associate alone, or that technically means solved for. Here you're going to make a substitute uh, the velocity um, for you're going to substitute the velocity you're going to substitute the velocity for I have to write this out. I can't type this, so it should look something like this. 2 pi r over t. All right. And then squared both sides. Alright, so that is what happens. The reason why they squared both sides in this case is just to get rid of the square root. Okay, so an intermediate step, if you can't see it, because again, the publishers didn't have enough room for this. So what they did here is they had the v square, they had v less than or equal to the square root of mu gr, right? Okay. The v became 2 pi r over t gr. Then they they squared both sides, right? So this cancels out, so they're going to square both sides here. If they squared both sides, it should look like this. 2 squared pi squared r squared over t squared. Because you see how the squared goes to both terms. Here this gets canceled. This just becomes mu GR. Okay, good. Oh, sorry. Uh, I can make this big R. Big R. It's the same R. Okay. Now you see how there's one radius here, one radius here. This cancels out. This cancels out. So there's only one left. That's how. This is the algebra to how they got this, right? They got 4 from 2 squared, pi squared. There's one R left, and t squared is on the bottom. Okay. There you go. All right. Okay. I'm gonna bring this equation down here so we could take a look at it. Okay. Bring it right here. All right. Okay. So, Blake and Carlos are trying to predict whether the coin will slip if the coin is too close or too far from the axis of rotation. The students follow reasons are followed. Okay. For each student statement, state whether the inequality written in Part B provides the statement to be true. If so, how? If not, explain why not. Ignore whether the student statement is correct or incorrect. All right. So here the student talked about, I think the coin will slip off if it's too close. If it's okay. So let's see if that's correct. If the coin is I think the coin will slip if it is too close to the axes. Not quite. So here, if when the coin is close to the axis, okay, and what they mean by the axis here is the axis of rotation. Okay, when the coin is close to the axis of rotation, then the radius is smaller. Okay, that makes sense. All right, so when R is a small value, that means okay. That means it is. Whoop, that means it's going to be less likely to slip off because it can be less than or equal to the coefficient of friction times the gravity. Okay, there you go. That's the complete explanation. Look at it. If R is small, okay, if R is small here, whoop, let me just make sure I have this for the other one. Okay, all right. If it's small, if this is small, uh, if this is small, right? This value overall is going to be what? Small. Can small be less than or equal to 2 mu times g? Yes. Okay. So the closer it is, so if this is some notes, all right? If the object is closer to the axis of center of rotation, right, it will be attracted to, it's going to be pulled into the center more, all right? What is attracting it going inwards is basically mu times g, gravity, right? So it's basically the gravitational force is pulling in the object. So here, if you want to think about it, watch. Here, if you want to think about this in terms of the strength of the gravitational field, think about this as like the complete center, right? This is the center, right? The gravitational strength here, right? Then think about this being less. So this is going to be less, right? Because it's further away. Then it's going to be more less, right? Then it's going to be more less, all right? So the gravitational strength, okay, the gravitational strength is less when when moving away from the center. All right. Does that make sense? The fact that it's less when moving away from the center. Okay? It's less when moving away. The gravitational strength is less when moving away from the center. All right? And that is the reason why if it's when the R is super close, right? It's less likely to go away, right? It's less likely to spill out, all right? But let's look at Blake's scenario. I think the coin will slip off if it's too far from the axis, right? Okay. All right. Let's see if this is right. I think the coin will slip off if it's too far away from the axis. That makes sense. It's like a merry-go-round. If I ride a merry-go-round near the center, I don't feel much force pulling on me on the axis. No, you feel more. If I ride near the outside, there is more force pulling me away. Ooh, 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 ooh. This is horrible. Oh. This is the worst thing ever. Oh man, I get triggered with this. There's more force pulling me away. Oh no. There's no centrifugal force. There's no force pulling you out. Makes no sense. All right. Okay. So let's see. What did Carlos get right though? Oh, in that end, his statement was wrong. It says don't correct this, but I had to just correct it. It's so bad. The last statement was so bad. So here he is right. Okay. When R is large. Okay. When R is large, uh, the left side of the equation increases. And the fact that the left equation increases, if the left side increases so much that the left side is no longer less than the coefficient friction times gravity. All right. So if this, let me show you this mathematically. So if this bad boy here goes up, so this becomes large. This whole thing is going to become large. But you see, oops, this whole thing is going to become larger, right? The fact that this gets large, can this still be true? No. If this goes large, it's not going to still be, it's no longer going to be less than or equal to mu times g. So this is going to break, right? That is why the further away you are, right, you're going to actually feel less of the gravitational pull. Therefore, you're more likely to go away or get away from its attractiveness, okay? But this might sort of make a little bit more sense when we talk about gravitational pull and gravity, right? It's going to make a little bit more sense on why some objects can escape their orbit. Okay, but this should explain to you why the moon revolves around us, right? The moon still revolves around us because why? Because 4 pi r squared over r divided by r squared. That radius that it has around Earth is actually very small. That is less than basically the gravitational pull. Okay, you can't really use this to explain that, but it's the same idea. Okay. All right, so just think about it. The further you are from the center, less gravitational pull. The closer you are towards the center, more of the gravitational pull. Okay? All right. So State whether the coin will slip off if it's too close or too far away from the axis. Again, it is too far when it's too far. All right? Okay? If it's too far, it will slip off. Why? Because it's going to feel less of the gravitational pull, or in this case, mu times gravitational pull. Right? All right, so Angelica and Dominic are arguing over the mass of the coin affecting whether or not it slips or not. Angelica believes that the lighter coin is less likely to slip because a lighter coin requires more force. Dominic believes that a heavier coin is less likely to slip because a heavier coin can have a greater amount of friction. And using your equation along with the physical principle, explain why the coin and mass is... Okay, so you look at the equation here. Mass cancels out. Okay? All right. Boom. So mass cancels out. Okay? All right. The uh, the attraction the how can I say it? The deviation? No, the force of friction times gravity is only basically influenced by the period t and the radius. So use your equation along with other physical principles to explain how the coin's mass affect its likelihood of slipping. So the mass doesn't affect whether it will slip or not. Okay? And in this case, the slip is defined by the pull strength of the centripetal force. Right? It is the sum of all the forces that is keeping it in the circle. Okay? All right? The only thing, oh, the centripetal, I don't know how to spell it, force that 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 the centripetal that is pulling in the coin doesn't rely on its mass. All right. Good. All right. There you go. That's part E. All right. So there you go. Those are all your solutions.